Okay, thank you. So now we will continue our discussion about the friction. So basically, in this part of the lecture, this part of the lecture will not be used in your first module exam. So we finish the material for the module exam until ideal Bernoulli. But in this part, we will discuss about the friction, the additional component later we need to put in the in the Bernoulli equation. Okay, please remember again that Bernoulli is assuming there will be no energy loss, right? There will be no energy loss. There will be no additional energy that we put into the system, and there will be no work done by the fluid flow. So that's what assumed by the ideal Bernoulli. In the real flows, actually the Bernoulli equation is not happening because during the fluid flow, the liquid or the fluid will have friction with the inside part of the pipe. So if the fluid have friction with the inside part of the pipe, there will be some heat, right, generated by the friction. And this heat will be released to the environment. So in this case, there will be some energy that lost to the environment. So for example, if you have straight pipeline with the constant diameters, so at point 1, at point 2, constant diameters. If the diameter is constant, then velocity will be constant, right? So if you have fluid flowing through the straight line, and if the fluid creates friction with the wall, there will be some energy lost to the environment. Then what will happen? The pressure will be decreasing along the fluid flow. Understand, right? Since in this straight pipeline, we assume the diameter constant, the velocity constant, then if we have, and the position are constant, right? Z1 will be equals Z2. Okay. Because there will be no change in the in the kinetic energy, there will be no change in the potential energy, then there will be loss in the pressure energy. Or we can say that pressure is decreasing along the flow. The longer the fluid flowing inside the pipe, what happened? The friction is higher. There will be more and more energy that lost to the environment. It means the pressure are keep lower and lower until sometimes the pressure will reach zero. And what happens if the pressure reaches zero?
Stops moving. Wait.
Yes, correct. So when the pressure reaches zero, the fluid is not moving anymore. So in the, for example, in the plant operation, in the factory, we do not need this happen, right? We do not want that the liquid or the gas as the part of the reactant, for example, we do not want that during the journey in the pipeline, it stops flowing. It needs to be keep flowing until it reaches the destination, for example, in the reactor or in the heat exchanger, for example. So if you have pressure drops during the flow, it means the energy keeps lower and lower. Then we need to put some additional equipment to increase or to supply the energy. Why we need to supply the energy? Because we want to keep the fluid flowing. The device is called pumps or blower. Pumps are for liquid, blower are for gas. Okay, so the function of the pumps or blower is basically to give additional energy, to supply and energy to increase the total energy of the fluid flow, so the fluid are keep flowing. Okay, that's the basic principle of the pumps and blower. And in this part of lecture, we still consider both liquid and gas are incompressible, sorry. It means the density will always constant. So for liquids, it's still incompressible, right? Because liquid are not significantly influenced by pressure difference. So the change of the density caused by pressure for liquid is neglected. And then for the gas, even though there will be some change in the pressure, right, due to the friction, even though there will be some pressure drop due to the friction, but since the pressure change are not really that high, there will be some pressure drops, the value are there will be some pressure drops, but since the change in the pressure drops are not really high, then the change in the gas density can be neglected as well. So for this case, we still can assume that both liquid and gas are incompressible, and also the flow are still in steady state. Steady states mean you can use the continuity equation, right? The rate of mass or the mass flow rate, inlet and outlet are the same. Okay, so this is the example how to use pump or blower. Basically, pump you can see at your house, maybe you already have the pump, right? It is used to get the water from the well. Do you know how deep is the well at your house? Anyone know?
Couple of kilometers, sir.
Kilometers?
I don't know, sir. I'm just guessing some numbers, sir.
Kilometers is 1,000 meters, right? No, I think most of it is like 60 or maybe 80 meters is already deep enough. Sometimes if you have a very good uh, earth water, then it's only like less than 10 meters. Okay, but it is under the ground, right? So, for example, the deep of your well is 20 meters, and then it needs to move upwards, right, at 20 meters, and then the potential energy will increase. If you assume the kinetic energy constant because the diameter of the pipe is constant, then if the potential energy increase, the pressure energy will decrease. Also, while the water are flowing inside the pipe, there will be some friction, right? So it will add some pressure drop as well. So when it reaches the surface of the ground, the pressure will be much lower. And then you need to put the water maybe in the water torrent, right? It's like above the house, like 5 meters above the house. So the energy of the pressure energy will keep lower and lower. If you do not install the pump, then the water will not flowing. Okay, that's why you need to put pump. And the requirement, how much you need the pumps and how much energy energy that needs to be supplied by the pump actually will be depending on the arrangement of the pipeline. Where is the water source? How far is it from the ground? And then where is the water tank? How high it is from the ground? And then how is the arrangement of the pipe? Arrangement of the pipe means how long is the pipe? Because the longer the pipe, then the higher the friction loss, right? Same as blower. So blower, for example, do you know the simple type of blower at home? Anyone knows?
I don't know, sir.
Do you have at home? See, at your room, perhaps?
Adanya hair dryer, sir.
Kipas angin, Pak.
Yes, fan, kipas angin. That's a simple type of blower, actually. So it's flowing the air, right? But in the factory or in the plant, normally blower are used to flowing the exhaust gas. Exhaust gas is basically the residual gas comes from the furnace. Furnace is the device to burn some materials, right? Maybe you need to react the materials in the furnace because you need to have higher temperature, and then from the combustion process, it will create some gas, and some of the gas maybe is not necessary for the process, so it needs to be flown to the air or flown to the environment. So basically, it will go to the gas stack. Either it will release or it will be burned, because if it's the gas is the combustible gas, then sometimes it will be burned in the gas stack. So how to flow the gas? You use blower. So the inside part of the pump, actually there are some types of the pump. Later when we discuss pump and blower, after this chapter, we will discuss about types of pumps and blower. The most common one that you use at home is centrifugal pump. So it will create, basically inside the pump, it will have blades. The blades are moving, creating centrifugal force. So when water are flowing inside the pump, it will have additional energy from the centrifugal force. Same as same as the blower. This is the basic types of pumps and blower. Okay, I'll move back. Actually, I have explained, right? If you have a straight pipeline and then you have fluid flowing from left to right, and the pipeline is in the straight pipeline with constant diameters, then what will be the effect of the friction? Friction force will be decreasing the pressure. So the profile of the inlet pressure and the outlet pressure will be like this. So this one is the pressure drop along a straight pipeline with the length L and for constant diameters. So again, constant diameters means you assume the velocity is constant. It's the same as the inlet and the outlet velocity. So the effect of the friction will be to the pressure drop. Okay. Now, how to correlate this friction to the pressure drops? Basically, first we need to analyze the flow. So since pipe are in the cylinder shape, like this one, right? So you can use the cylindrical coordinate. Cylindrical coordinate is x, r, and theta. X is, do you still remember? This is the axial direction. Axial direction means along the pipe, same direction as the fluid flow. That's what we call axial direction. And then the second one is radial direction. Radial direction means along to the radius. And then tangential direction. Tangential direction is like this one, right? So this one. So along the tangential direction. So for this one, for deriving the correlation between friction and the pressure drops, we just need to analyze position in axial and radial. Okay, I'll redraw so this one is axial, this one is radial. Okay, if you take vertical straight line here, it means in the vertical straight line, all position in the vertical straight line will have the same axial position, right?
Yes, sir.
Yes. Okay, then now we need to define what we call axial velocity or UX. Axial velocity is the velocity at axial direction. On the same position, on the same axial position, you may put, for example, two different positions, right? One is closer to the wall, one is further to the wall. So between these 2 points, even though the axial position is the same, but the radial position is different. Okay, so we can define axial velocity at the axial velocity at some radial position or at R position. Misalnya di sini. Ini pusat. This one is the center of the pipeline. Okay, this one is R, arbitrary position, and then the length or the distance between these 2 points are delta R. So this one is axial position, axial velocity at R, and above that is axial velocity at R plus delta R. That is the notation. Can be understood, or do you need some clarification?
So far it's okay, sir.
Okay. So now, because we have 2 positions with the same axial position, but different radial position, then we can write down what we call velocity gradient. What is velocity gradient? Velocity gradient is actually the differences of velocity due to different R. Because velocity at point R and velocity at point R plus delta R is different, right?
Yes, sir.
Okay, which one is higher?
R, sir.
Why?
Because it's further from the wall.
Yes, it's further from the wall. So the effect of the friction is lesser. So we can call it this one velocity gradient. Okay, so just read the below sentence. Because there will be because there is contact between the fluid and the wall, and then the wall will give friction force with the opposite direction of the fluid flow. Okay, the higher the distance of the point from the wall, then the value of the friction force is lower. That's why the velocity is higher. That's why you will have the velocity gradient. Okay, any question first about this one? Okay, if there's no question, then I'll move on. Okay, I'll draw again. Sorry. I think it's better to use. Okay, so if the flow is like this, and this is the axial position, and this is the R position, what will be the direction of the friction force at point R? The direction.
Ke belakang nggak sih, sir?
Yes, it should be opposite of the flow direction, right? This is friction force at R. To calculate the shear stress, if you have friction force at point R, then you have to divide it by the area, right? And then how you calculate the area?
2 pi r times the length.
Yes, this should be the surface area of the pipe, but not the whole pipe, only until the distance of R. So should be this one. So this is the friction area or on the fluid layer at the distance R from the center of the pipe. L is pipe length. Okay, this is the friction force at point R divided, sorry, this one S, divided by the surface area. We call it shear stress at axial direction, but at the point of R. Can be understood? So this is the shear stress at axial direction. The direction is axial, so along the pipeline, but in the opposite of the fluid flow.
Sir, how do we find Fs, sir?
Or later.
Okay.
Actually, it's not possible to calculate by the experiment. So we need to correlate it with other parameters. But from here, you can correlate the friction stress or shear stress Actually the same, right? Shear stress or friction stress is defined as the friction force per friction area. This is at point R.
Sir, if that's the case, then what's the difference between shear stress and frictional force then, sir?
This is the friction force. This is the shear stress. Stress is force divided by area, right?
Oh, okay, okay. So it's basically like the loss in pressure gitu, sir. Something like
Yeah.
that. Is it right? Okay.
But for the pressure, the area is the cross area, right? This one is the surface area. Okay. So tau Rx is shear stress at axial direction at point R. If you change the position of R, then the tau Rx will be different. Tau Rx will be different. Shear stress will be different. The velocity will also be different. And the tau Rx will have correlation. Please remember again, will have correlation with the velocity gradient, right? Because if you change the R, velocity gradient means the change of the velocity due to the change of R. The change of the velocity at axial direction due to the change of R. R is the distance from the center of the pipe. Since if you change the position of R, the velocity is different. There will be gradient, there will be velocity gradient, and then the value of the tau Rx will be different. However, for some types of fluid, we call it Newtonian fluid. Hopefully you remember the ratio between tau Rx divided by velocity gradient is always constant. Constants become the viscosity. Why minus? Minus are showing. Do you still remember why we put minus sign here?
Does it show the loss in energy, sir?
Not the loss of energy. This is showing the different direction between the velocity and the shear stress. Because if the velocity are on the right direction, the shear stress will be on the left direction.
Bentar ya, sir.
Why?
Lagi sambil ngeliatin yang kemarin, sir.
Okay. So basically in this formula, the minus signs showing the different direction between the shear stress and the velocity gradient, because both are vector, right? So both are having direction. So we put minus sign over here. But anyway, don't be confused with the sign. Please remember the concept, okay? From this slide, basically, how you can calculate tau Rx, how you can calculate shear stress is by calculating the shear force divided by the surface area. It will be depending on the position in radial position. It will be depending on the position of small r. It can be in the middle of the pipeline. It can be at the wall, or it can be in between, right? Different in or in the same axial position, right? But you can put a different position of R. In each position of R, the value of surface area will be different. And then the value of shear stress will be different. And then the value of the velocity will be different. Any question first? Okay.
Or it's okay, sir.
Should be okay, right? Okay. Then there will be two extreme case, right? First, at the center of the pipeline. At the center of the pipeline, R will be 0, right? At the center, R will be 0. Because R is 0, then there will be no velocity gradient. Velocity gradient will be 0, and the shear stress will be 0. It means will be maximum. Okay. The other extreme are when the position of R is exactly at the pipe wall. When R equals big R. When the point are in the pipe wall, R equals big R, then the velocity gradient will be maximum, shear stress will be maximum, and basically shear stress at the wall, so tau W is shear stress at wall. Basically, you can correlate with the velocity gradient at R equals pipe radius. This is just a notation. It's the same like this one, right? It's the same with this one. But for this one, we put the point at arbitrary R, anywhere along the pipe radius. But exactly at the pipe wall, when R equals pipe radius, then you just replace with this equation. Equation is the same actually, but the notation become shear stress at the wall, tau W. Okay, any question first?
Sir, if viscosity is higher, wait. If the I'm confused now, sir. Because both values of TW and DU over DR is large, right, sir? Is that true?
Sorry again?
The value of TW and DU over DR, is it large, sir? In the case of the wall?
Yes, this is the maximum value.
Then how does it affect with the viscosity again, sir? Because
Viscosity will always constant, right?
constant, eh?
If the fluid
Yeah,
is
benar juga.
the Newtonian, the ratio will be constant. So the value of mu will be constant.
Okay.
Anywhere along the radial position. There is no influence of R position to the viscosity because the fluid is Newtonian. So the value of mu is always just one value. It means since the value of mu is constant, if you increase the shear stress, it means you increase the velocity gradient.
Because they're talking about the same fluid, right, sir? That's why the
Yeah, yeah.
viscosity will always be the same, right?
Yes, yes. Because
Okay.
we do not change the fluid, right? And the fluid is Newtonian. So we just see the change of the position. If you analyze, because you can imagine fluid is like layer by layer, right? That's why you can put the R in the middle where R equals 0. or this one, or this one, or this one, or this one, where R equals R. The fluid is the same, only the position of the layer are different. And each layer will have different velocity. That's what we call the differences of the velocity in each layer. That's what we call velocity gradient, dux over dr. That's what we call velocity gradient. So for both extreme, this one and this one, in the middle, there will be no velocity gradient at all. In the middle, exactly in the center. So velocity gradient equals 0, and the shear stress will be equals 0. How about the others? When r equals pipe radius, there will be value of the velocity gradient, and there will be value of the shear stress, and both are maximum. Velocity gradient maximum means what?
The velocity is the least.
Yes,
Yeah,
the
that's it.
velocity is the lowest.
Yeah.
Correct. So basically, then you can write down at the wall, the shear stress will be noted by tau wall. The velocity gradient is maximum. The tau wall is the maximum shear stress. And also the velocity gradient will be maximum. Mostly in this case, we can say that velocity at the wall will equals 0. Okay. If you notice then what the velocity gradient's physical meaning basically by seeing these figures. Apa arti fisik dari velocity gradient? What will be
It's
the
like
physical meaning of the velocity gradient?
it's like the difference in velocity regarding the radius, right, sir?
Yeah.
Because in each point of the radius, the velocity will be different, right? Caused by the shear stress.
Okay, so if you take the gradients, it means you take the delta, right? You need to compare it with the some value at some point. So basically, the velocity gradient means the velocity at arbitrary position of r comparing to the velocity at which? At the center of the pipeline. So you can interpret the velocity gradient that way. At certain r position, you will have velocity. The same axial, of course. Yeah? At certain r position, you will have velocity. So you compare it, this velocity with the velocity when r equals 0. So the differences will be what you call the velocity gradient. The higher the velocity gradients, it means the delta is higher, right? So it means the r is more further from the center. Can be interpreted that way also. Can be understood or still confused?
Yeah, understandable, sir.
Okay, that's the concept of shear stress and velocity gradient. That's the correlation between shear stress and velocity gradient. Okay, now before this part, I'll go to this first. Okay, please remember again that due to the shear stress, due to this friction force or shear force will create shear stress, right? Then shear stress will create the velocity gradient. And then the shear stress will also create the pressure drop. Okay, then how to correlate the shear stress with the pressure drop? Then you need to make the force balance. The force balance is basically the big pipe. The big pipe, okay, big pipe. Big pipe is the outer pipe. Length is L, and then radius are this one. Okay, to make the force balance, you can create the segment of the pipe, which is this one, the small pipe inside the big pipe. Okay, for example, at the inlet of the segment, right? Not the big pipe. So at the segment, the inlet part you note it as X, and then at the outlet part you note it X plus delta X. So it means the length of the segment is delta X. Okay, now do you still remember the force balance equation or any balance equation? Accumulation will equals
Input minus output.
sorry
Input
input
minus output.
minus output plus generation
Plus yeah, generation minus consumption.
minus consumption. Okay, because we are talking about steady state flow, the flow are steady state, so there will be no accumulation. Okay, how about generation and consumption? In this context, is there any force generated or any force consumed?
Is it the pressure force there?
No, no, that's not. Pressure force is the input and output. But during the fluid flow, please remember what I have explained to you. Is there any other types of force that generated or consumed during the fluid flow?
I don't think so, sir.
Are you sure?
I don't know anymore, sir.
I already explained to you just now. What other types of force that happen during the fluid flow?
Shear?
Hmm.
Shear is being generated, sir.
Yes,
Shear force.
shear force are being generated. But in terms of adding or decreasing the energy, it will be adding or decreasing the energy, the shears?
Maybe decreasing, sir.
Not maybe. Yes, it is indeed decreasing the energy because it's lost to the environment, right? So you need to remember or understand the concept. So for this one, sigma f will equals 0. So force inlet minus force outlet, since friction force are decreasing the total force or the total energy, is basically the same, right? Minus force shear should be equals 0. Okay. Force inlet is basically the pressure force. So at position X, inlet force will be this one. Pressure at X times area at X, the cross area at X. Okay. How about the pressure outlet? Pressure outlet, oh sorry, the force outlet is also the pressure force. However, it is the pressure at X plus delta X times area. But area is the same, right? So times area. Because the segment is a cylinder, so the inlet area and the outlet area should be the same, which is PR squared. R is the radius of the small pipe. Okay, and then sigma F equals 0. Sigma F is inlet force minus outlet force minus shear force or friction force. Then you can write down this one. This one. This is the sigma F equals 0. So if you put the friction force to the right, then you can get this one. Then you change Fx and Fx plus delta x into this one. You have this equation. Until this part, do you have any question?
So, sir, this frictional force is that force that we have to find to put in the formula of the shear stress, yes, sir? Is that right, sir?
Sorry. Can you repeat again?
This frictional force that we're trying to find is the force that we will input inside the shear stress formula, benar nggak, sir?
Yes.
Okay.
So F friction is this one. Basically, F friction is this one. Same. Too much coretan. So F friction is this one. Same. Okay. So until this part, can we understand, right? Okay, then we define delta P. Delta P is outlet pressure minus inlet pressure. Because the inlet is higher, then the value will be negative, right? And then friction force will be tau times surface area. Surface area for the friction will be 2PR delta X in the segment. But the cross area will be PR squared. Okay, from this one, and then you can go to this equation. And by combining this equation from left and the right, you will have the correlation between the shear stress and the dpx per dx. What is this one? What is the physical meaning of dpf over dx?
The difference in pressure as throughout X, is it, sir?
This is called the pressure difference along axial position. It means the tau Rx will create the pressure difference along axial position. This is to explain the previous figure, that this one, like pressure, axial, this one. It will be depending on the value of R. Okay, any question first? So this correlation you can get from the force balance equation. There will be two force component in the force balance. The pressure force, which is the inlet force and outlet force. And then the other types is the friction force. The pressure force is pressure times area. Okay, the friction force is the shear stress times the surface area. Then by combining this equation, you have the correlation for the shear stress and the pressure difference in axial position. Okay, any question? Oke, cukup jelas ya. Hopefully it's clear enough. Okay, then so force, what will be the unit? Shear force or friction force, what will be the unit?
Joule, sir.
Force,
Force, Newton. Oops.
Newton. Please be careful. And then, what is the unit of shear stress? It will be force divided by area, right?
Area,
So
yes.
Newton per
Meter square.
meter square. Okay. We have discussed before that when the fluid have friction with the pipe, it will have the friction, right? It will have friction, and the friction will create the heat, and the heat will be lost to the environment. So basically, in the fluid flow, the friction force will be transformed into the friction heat. Heat is energy, right?
Yes, sir.
Heat is energy. So basically, how to calculate the friction heat is by calculating the friction force times the length that fluid has been traveled, or delta x. Just remember, energy is force times distance. In this case, it's the same. The friction heat or friction energy is the friction force times delta x. The unit will be the unit of energy,
Joule, sir.
joule. Or since it's force times delta x, can be Newton meter. Okay. So you can express the friction as friction heat with the unit of energy, joule. You can also express the friction heat as friction heat rate. If you heard the term rate, it means you divide it by time, right? So the unit will be joule per second. This one is heat rate, friction heat rate. And please say that friction heat rate is friction force times delta x divided by delta t. Then this one becomes velocity, right?
Sir, isn't it the same thing as power, sir?
Yes, yes. But in this context, we do not call it as power. Not power. Joule per second is what? Power?
Yes, sir. The unit is watts, if I'm not wrong.
Oh yeah, yeah, correct, correct. Yes, yes. But this one is not as a power because it's like how much energy that lost by the friction per time.
Oh, okay, okay, okay. Because it's not the amount of energy that you gain, but you lost, right? That's why
Yes,
it's not
correct.
power. It's okay.
But later, the loss of the energy need to be compensated, right? Need to be compensated, need to be added to the system again to maintain the fluid flow. You are using the pump, for example. So if you are using the pump, that the concept become power. Energy that you need to supply to the system per unit of time. But for this one, it's easier to understand it as how much you lost per time. That's the friction heat rate. How much energy that you lost over the time. Okay, this one. To make things more interesting or complicated, sometimes or in the fluid flow calculation, the friction energy can be expressed as specific friction energy. Specific means you divide it
Mass, sir.
by mass. So if you have friction heat rate, then you divide it by mass flow rate. But if you have just friction energy, then you divide it by the mass. Okay. Until this part, do you have a question? If you do not have, I think I already told you to have the paper and pen. So now try to derive this one, right? EF is friction specific energy. The unit is what? Joule per kilogram. This one is this one, right? And AF is FF delta X. This one is rho times V. Okay. Then V, remember the segment of the pipe. So P R square times delta X. Okay. Now, based on this equation, and you will have this one, FF is tau R X times 2 P R delta X, right? And tau Rx R R over 2 minus dP F per delta, ya, delta PF per delta X from this one. Try to combine this into this equation so you can get this one. Please try. So please find the correlation between EF as a function of delta PF and also EF as the function of tau Rx by using this equation. Okay, I'll give you 5 minutes. Is that enough?
Okay, sir. Benar, sir.
Okay. you should get, please check, you should get that EF will be minus delta PF over rho, same like in the box, or as the function of tau Rx should be 2 delta X tau Rx per R rho. Dicoba ya, please try. Okay, anyone got the same result?
I got the result already, sir.
Okay, for both?
Yes, sir. I got EF equals to negative PF over density.
Okay, and for the correlation between tau Rx, for this one?
Oh, I haven't gotten that one, sir.
Yeah, just try it as well.
Wait, sir.
Yes,
What do we do after we find it?
just check it whether you get the same result. So as EF, if you replace it by delta PF, should be EF equals minus delta PF divided by the density. But if you correlate between EF, small EF, and tau Rx, should be 2 times delta X times tau Rx divided by R, small r, times density. Is that correct?
Hold on, sir.
Okay.
I got it already, sir.
Okay, is that the same?
Yes, sir. It's the same.
Okay. For the others, please try it. Okay, so this is the
I
basic.
also think, sir.
Sorry. Yep.
I also got the same.
Okay, then the equation should be okay. There is no typo in the equation. Okay, now EF is the specific friction heat. The unit is joule over kilograms. If you calculate EF exactly at the pipe wall, then the equation becomes this one. At the pipe wall, tau Rx becomes tau wall, and small r becomes big R. And D will be equals to 2 times R, right? Then you will have this equation. Okay, now please remember, because EF, small EF is specific heat or specific energy, then if you calculate or you write down the Bernoulli equation, you will have this one, right? Correct? Okay,
Yes, sir.
this equation is only for ideal Bernoulli. Now we already know about the non-ideality comes from the friction in terms of EF. Now in this Bernoulli equation, where do you want to put EF? On the left or on the right? And what will be the sign? Is it plus or minus?
It should be minus, sir. But I'm determining where to put it.
If the sign is minus, you put it on the left or on the right. So position 1.
I think it's on the right then, sir. Because position 1 is ideally in the middle, right?
No. 1 is inlet,
Salah ya?
2 is outlet.
Oh, outlet ya itu.
This one, right?
Oke,
So
oke.
if you analyze the Bernoulli in the inlet and outlet of the pipe flow, so where do you want to put the EF? on the right or on the left, plus or minus?
I think if it's minus, it's in the left. If it's plus, then it's in the right.
Why?
I just think of it like it has to be balanced.
Yeah, yeah. So,
Because P2 will be less than P1, you know, sir.
yes, correct. Because if you have energy that lost, it means the energy that comes into the pipe will be higher than the energy that comes from the pipe, right? So the energy input should be higher than energy output. So if you put on the left, then it becomes minus EF. Can you put it on the right? Can. But if you put on the right, then it becomes plus EF. But just please understand again the concept. The EF is the friction energy, specific friction energy. It will be decreasing the total energy of the system. It means when we when we have the fluid flow flowing into the pipe due to the friction energy, the total energy will be decreased. It means the outlet energy will be lower than inlet energy. The outlet energy is this one. The inlet energy is the left one. So if you have EF, then it will be decreasing the inlet energy. So if we take the delta, like please do not consider W because we haven't considered about the pump. It's only the friction. So if you take the delta, delta means 2 minus 1. This one Z means delta Z means Z2 minus Z1. This one is P2 minus P1. But please be careful for this one. This one is U2 square means U1 square. Ya, bukan not U2 minus U1 square. Just like this. Okay, now you already know that's from the Bernoulli ideal, which previously only take account 3 types of energy. Now we introduce friction energy. If you use all in a specific unit, then and specific energy, the friction energy, specific friction energy, small EF, then you can put into the Bernoulli equation. It will be decreasing the input energy. You put minus EF in the input because it's decreasing the input energy. I think should be clear, right?
Sir,
Yep.
can I also put it in a view in which accumulation has to be 0, sir?
Accumulation is which one? This one is steady state, then the accumulation is always 0. Accumulation 0 means the total energy should be same inlet and outlet. But this one, in this case, we already know about the energy that lost to the system. So we need to take account the energy that lost as well. The
Okay,
accumulation is
sir.
always 0
Yeah.
because it's a steady state flow.
Thank you, sir.
Okay. Any other question? Okay, if there is no more question, we will continue on next week. Thank you very much. Good afternoon.